through, basically run through 3 different examples. The first one, I will have to determine the contributors because I'm going to be rejecting. The second one, I will not be rejecting, so I will get to skip doing the contributors because I will not be rejecting. And then the third one, I am rejecting, so I will have to do the contributors again for the third one. You can feel free to, not watch all the examples, but, I definitely would probably watch the first one at least, just because that one I do find the contributors on. So let's do this. Okay, we have a sample of 8,474 people. We're going to be looking at their blood pressure for 4 years, and they were free of heart disease at the beginning of the study. We then take this anger scale at the end of the 4 years to see, what's their anger scale, and we compare this to over that 4-year period, did they develop heart disease? So we want to know if there's some kind of an association between heart disease and the anger level for people. So this is going to be a test for association independence, and we would have to go through our conditions, and because I think you probably can do those, I don't want to waste a lot of time on that. We would have to go through and be random. I would say that this did say that there was a random sample of people, so that's given. We would need to be independent. And I would say that we are meeting the 10% condition on this observational study, because this is not an experiment, this is observational. We haven't applied treatments to people. And then we would need to know the large enough condition, and that would be based on our expected counts, which we would want to get from the calculator. So we would want to put this data into our calculator as matrix A. That would be our observed counts, and we would then generate, using the test, we're going to generate the expected counts. And my null hypothesis is going to be there is no association between anger level and heart disease. And my alternate hypothesis is there is an association between anger level and heart disease. Okay, so I'm going to put this data into my calculator. You can see my chapter 1, what I might have done for conditional distribution of this. But I'm going to put this into my calculator and see what happens. So going into matrix, and you would go over to edit, and I have already entered this matrix in. It was a 2x3. I've entered the numbers in. I am going to hit second mode to get to quit. So I'm out. Now I'm going to run the test. Got to scroll all the way down to the chi-squared test. Select it. I have my data in matrix A. Wherever you have entered your observed counts, that's your observed. The calculator will generate the expected counts. And so let's write down this chi-squared. That's the sum of the chi-squareds. That's the p-value, very, very small, essentially 0. This is the indication that I will need to generate all the chi-squareds, all those chi-squared contributors, because I need to know what was the item that contributed the most to that 16.0767. Okay, so let's write down our expected counts. We're going to write those down because that's also part of the proving of the, actually I'm going to go over to edit because I prefer to like look at it this way. So I've gone over to edit and down to matrix B. So yeah, you need these expected counts to be able to show that you checked the large enough condition. So let's go back, write these down. Okay, so, and I'm going to, because I know that I have to do the chi-squared contributors, I'm going to write this down in a table format instead of writing the matrix, because I know I'm going to have to do the calculation. So here are my expecteds, and so I'm going to write them down. Observed 53, 3057, 110. 4621, 27, 606. And this is the way I would enter it into my calculator for doing the contributors. Okay, so these are the numbers from the matrix, and I'm maintaining the same order as I did for the writing of the observed so that they correspond with each other. 4624.9, 14.193, and 618.081. And then I'm leaving myself a spot to put my chi-squareds. And since I've entered these in my calculator, this is my L1, this is my L2. Remember this from goodness of fit, finding the chi-squareds this way. Just makes it a little bit easier. I do know already that my sum of my chi-squareds is, let's see, let me just move this up, is 16.0767. I know the probability that my chi-squared goes above a 16.0767 is extremely low. It was 3.228 times 10 to the negative 4. That was with degrees of freedom of 2, because the calculator, remember, will calculate that for us. So if you look at these chi-squareds here, if you look at these numbers and compare these numbers to each other, I'm thinking that this one's going to be a major contributor just because of the 27 is like basically double 14. So that's really, really off, more off than any of the other ones. But let's see what the calculator says for those contributors. So I have already entered these things in my list. There's my L1, my L2. I'm going to find the chi-squared. Remember the chi-squared, and that's on your formula sheet right here. It's on there. We need to take the L1, and I'm putting in parentheses, minus the L2. We're going to square it. Then we're going to divide by the L2, and that's going to give us all of our chi-squareds. And just as I expected, that category right there is really the largest contributor with 11.556. So I definitely need to highlight that. This one is less than half of that, but you know, that's where the second most is. But like that is really overwhelmingly what is causing the rejection of this null hypothesis right there. So I'm going to highlight that in my analysis. Okay, 4.0144, 0.0917, 0.1449, 0.0033, 11.556, 0.2361. So now let's write our conclusion. Since the p-value of, let's see here, 3.22 3.222 or 28 times 10 to the, I mean, really, we could just call it 0, is less than alpha equal 0.05. We reject the null hypothesis and there is significant evidence that there is an association between anger and heart disease. So we should keep ourselves calm. Disease. The largest contributor was, let's see why is this happening? Largest contributor was, who were those people? Those 27 people were the high anger people who ended up with heart disease. So high anger really seems to have a result. Moderate anger, not so much. High anger was high anger with high heart disease, developing heart disease with remember always support, I was about to write always support with a number. So with a chi squared equal to 14 point, oh wait, no, that's the expected count, with a chi squared equal to 11.556. So I would definitely tell people who have high anger to, get some help, because there seems to be an association with that. Next example is looking at cell phones and landlines. They have separate samples. They're looking at the cell phones. They're looking at the landline users. They want to know if there's a difference for these political party affiliations based on their different type of phones. And so we're going to look at that. And if you feel like you know what's going on, you probably can realistically pause this. But, basically the idea is, could you tell that this was a test for homogeneity? Okay. Can you go through the conditions? Random. It was given. SRS. Is it independent? Now it is observational data, so the 200 is less than or equal to 10% of N is the more appropriate test, and I would say that there are over 2,000 phone users. I could have checked the categories separately, but there's definitely over 2,000 phone users. And then we would want to check the large enough condition. And in order to check that, at some point, we need to write down our expected counts, because we need them all to be over 5. Remember, if they are not over 5, we need to combine some categories greater than 5. So I go to my calculator, and I have the calculator generate this. I already know that this one is going to be we're not going to be rejecting, so I am going to put my expected in a matrix, and I'm just going to keep it reported as a matrix. And so I'm going to get those right there, and that's going to support that condition. You always do need to write what your expected counts are. This time I didn't put it in a table because I already know that I'm not going to be rejecting. So, okay, so second matrix, edit. I've already entered in this matrix. Let's just make sure it looks right. Looks good. I'm going to hit stat test, go down to the chi-squared test, where I will then run the test, calculate it, and there's my chi-squared, the sum of the chi-squared contributors is just a 3.2199, which is basically 0.200 at 2 degrees of freedom. So that is not resulting in rejection. So I am going to then go to my matrix and go to edit, go down to matrix B and write down these expected counts as supporting my conditions. However, I will not need to go through and find the contributors since I'm not going to reject. Let's write these expected counts: 46.08, 20.16, 29.76, 49.92, 21.84, 32.24. So I've done that. Now that means I have my conditions met. At the beginning of this problem, I did write that I am doing homogeneity. T. Okay, and so let's write our hypotheses. Hypothesis, so remember homogeneity is about being a difference. So there is no difference in political affiliation based on phone service type. And the alternative hypothesis would be there is a difference in political affiliation based on phone type. And so then we got the sum of the chi-squareds from our output was a 3.2199. The p-value, the probability of a chi-squared going above a 3.2199 was not that small, 0.19989, which we could call that 0.200. And so then I will draw my conclusion, and I won't need to do any follow-up. So I will draw my conclusion. Let's see, let me make some more room here. Okay. Since the p-value of 0.200 is greater than alpha equal 0.05, we fail to reject the null hypothesis, and there is not significant evidence that there is a difference in political affiliation based on phone type, land, or cell. phone. Okay. And then there was no follow-up analysis needed on that. I did not need to get the chi-squared contributors. And one more example, if you're interested in watching it, one more example where we have an experiment. So that helps us with our independence condition. Last example. Okay, we've got cocaine addicts, and they take these 72 cocaine users and they split them up and they give them a treatment. There's desperamine, lithium, and then the placebo, which of course should do nothing, but sometimes we have a placebo effect. But so then they look at them after some amount of time to see if there is a relapse in their cocaine use. So if they have a relapse, that's not a good thing. If there's no relapse, that's a good thing. And then you can look at your chapter 1, the graph right here that we could have created with our chapter 1 methods. And of course, those would have been based on the drug treatment. So these would have been based on going, like for example, this one right here would have been, it would have been 10 out of 24 because it's going based on the total for the treatment. So that's why it would be out of 24. And this one right here would have been 18 out of 24. And this would have been 20 out of 24. Because remember, they split those groups into even groups. So that's how they would have done that using the chapter 1 methods. Think of what you're basing your situation on. And this would have been based on the treatment use. So the treatment totals would have been our bases for our percentages. But anyway, we're going in and we're going to do because we split them up first and then did this is a homogeneity test, chi-squared test, as long as our conditions are met. And so we did randomly assign them to treatment, which actually, because of the dependence, because we had random assignment to treatment, then we actually are meeting independence. Experiment with random assignment. That's actually enough to achieve independence. And then we need to be large enough with our expected counts greater than or equal to 5. Now I know that this is going to be a situation where we reject. So what I would do is I would right away start getting myself set up. I mean, really, when you run the thing, you run the matrix, see what the p-value is. As soon as you see you're going to be rejecting, then you're going to be setting up this 8, 10, 18, 20, 14, 6, and 4. And then what would we get for expected? So let's have the calculator let us know. Okay, let's go to our matrix. We go in, we make sure that we've entered in the data. It was a 3x2 matrix. Then I quit, go into stat, tests, go down to the chi-squared test, tell it that matrix A is observed. They're going to generate matrix B for us, calculate, write down what the sum of the chi-squareds was, write down what the p-value is. Because this is lower than 0.05, we're going to be rejecting at a degree of freedom of 2. And so let's just look at what our expected counts were, because remember, you always do need to write those down in order to prove that you actually checked the large enough condition. So into my matrix, and this time I'll just call up the name, and there it is, matrix B, calling in the name, and it's a pretty simple matrix, what you're expecting to see happening. You basically are expecting to see twice as many relapses as non-relapses, but then we can look and see what the chi-squared contributors would be, because I can put the 16s and the 8s into my calculator under edit. See, there's my data that I've got, my observed counts. I've got my expected counts, make sure that they're matching up with each other. I'm going to calculate my contributors, L1 minus L2. That quantity needs to get squared. Then I need to divide by my L2, and those are the chi-squareds. The largest contributor is definitely the dyspromine no relapse. We seem to be doing much better in that category than we expected to see happen. We can also see that these two categories are basically half the contribution of that one right there. So let's write about all this information that we have. Our expected counts were 16, 16. Why is it slanted like that? I don't understand it. There's the 8s. Now we want to write down our chi-squareds because we know we do need those for our follow-up analysis. You may mention that one, but the main one that we do need to definitely mention will be this 4.5. That one's extremely, or like, is the largest contributor, although together with those other two, it's, contributing over half, because the sum of the chi-squareds is equal to 10.5. The probability that a chi-squared goes above a 10.5 is 0.00524. I never did write my hypotheses, did I? So let's make sure we write those. The null here, it is a homogeneity situation, so there is no difference in cocaine relapse for the 3 treatment groups. And the alternatives, there is a difference in cocaine relapse for the 3 treatment groups. Since the p-value of 0.00524 is less than alpha equal 0.05, we reject the null hypothesis. Check. Hypothesis. And there is significant evidence that there is a difference in cocaine relapse for the 3 treatment groups. The largest contributor was desipramine, I don't know how to say it, with no relapse, chi-squared equal to, let's see, that was 4.5. And I mean, those other two groups being kind of involved in this process of rejecting, maybe I would mention those two, that also the desperine relapse was lower than what you expected. But also, strangely enough, the placebo with no relapse also seemed to, had a chi-squared of 2. So that was kind of interesting as well. Also, desperamine with relapse was chi-squared equal to 2.25, and the placebo with no relapse was chi-squared equal to 2, which was kind of surprising right there.